We are continuing our problem session or organic chemistry tutorial on alkenes. This portion of the video will show you just an introductory part of the alkene chapter, where we cover naming and identifying different biological properties of alkenes, and also the structure to name or name to structure conversion, and so on. But in the next few videos, I will also cover the reactions of alkenes, which is very broad in terms of several reactions that an alkene undergo. So this is part of a continuation that we have in the previous video. Now I want to continue by doing this problem. It asks us, show two enantiomeric pairs for 4-methyl 2-nonene. This is a 9-carbon alkene compound. So the first question is asking us to have two enantiomeric pairs for this compound. And the second question is to show 4 diastereomeric pairs for 4-methyl 2-nonene. So if you see this naming, 4-methyl is, you start counting from the shortest path to the alkene, which is this. This is at 2 position. You have the ene, which is the alkene, 3, 4. Actually, this is 1, 2, 3, 4, F5 actually. This is a 5-methyl position, sorry. This would be a 5-methyl position. 1, 2, 3, 4, 5, 6, 7, 8, 9, nonene, it's a 9-carbon. And we're going to show two enantiomeric pair. The enantiomeric pairs would be referring to, not to the alkene in this case, but to the stereogenic center here. This carbon over there, what you see is a stereogenic center. It could have an R or S. That's why we have two enantiomeric pairs. So if you were to show two enantiomeric pairs for this, two pairs in terms of R and S for this, R, S, but also this is one pair. You have an R and S, and this is, for example, an E configuration. So you would have for E, and for Z you would have R and S. So these are enantiomeric pairs. This is one pair for R and S, and this is one pair, R and S. So, for example, if I do this for the E, I would have one would be up like this, and down the methyl group, this. So this is both E and E, it's referring to the alkene, but here that should be an R configuration, and this is an S configuration. I want you to figure out that. So I have one pair here. Other pair would be, the second pair would be the Z. When it comes to the Z, it should be something like this instead of that way, so that I would have this, that is right there, and the rest would be the same. So this is an R for the Z, and for Z again you could have an S as well. So that would be a methyl group down, that is an S. So this is one pair, and when this is one pair, the relationship between this pair, these two pair is enantiomeric. These are also enantiomeric. So there is no enantiomeric relationship for the alkene. The alkene is a stereoisomer where the cis, the E and Z are called diastereomers. So now we are asked to show four diastereomeric pairs. Four diastereomeric pairs means that, so this is a 2E, 2Z, and 5R, 5S, 5R, 5S for Z. So these are all 2E, 2Z, 2Z position, and the stereomeric centers are, stereogenic center is at 5. So I will just list down all the diastereomeric pairs that are possible. So you could have 2Z, you could draw out all this, 2Z, 4R, 2E, no, that's 5R, sorry, and 5R. This is one diastereomeric pair. They are diastereomeric. They are not mirror images, as you see. They are Z and E. That's one pair. I want you to draw this structure. And the next would be, you can have 2Z, 5S, and 2E, 5S as well. That's another pair possible. As the question refers to 4, so I am still to do 2Z, 5R, 2E, 5S. So 2Z, 5R, okay, so that is the third one, pair. The fourth would be 2Z, 5S, and 2E, 4R. No, 5S. 5R actually. Sorry for that. So this is one diastereomeric pair, second, third, fourth diastereomeric pair. The relationship is not enantiomeric for this one. This and this are diastereomers. This and this are different diastereomers. This and this are different diastereomers where you have 2Z and 2E, but 5R, 5S, 2Z and 2E and 5S, 5R. So all of this are the four diastereomeric for 5-methyl 2-nonene. Nonene because it's 9 carbon, ene because it's an alkene. So this is just showing that the combination of enantiomeric relationship and diastereomeric relationship. So always remember the E and Z relationships is diastereomeric. That is the whole point. They are diastereomers. E and Z are called diastereomeric. They are not mirror images. So that's the main point we want to show in this exercise. So these are enantiomeric pairs because they are the same on the E and the same on Z. So these are enantiomeric pairs. Enantiomeric. They are only differing at the stereogenic center, right here and right there. So the relationship between this is enantiomeric pair because they are the same on the diastereomeric part. So we're going to continue more with more problems. Okay, here are interesting questions that are, why are these incorrect names? There are names given and you're going to check how they are named and say why they are incorrect names. and will give the correct name or the correct structure for this. So the first one is cyclohex for all. So the idea is meant to show that you have a cyclohexene and you have, at fourth position, you have an alcohol, all, for all. So 1, 2, 3, 4. That's possible, but it is probably the problem with this naming is that you should show where the alkene is. That means you should name this cyclohex 1N, 1N. So the correct naming for this would be cyclohex 1N for the alkene and for all. So that would be, I think, the right naming for this. So this misses where didn't show where the alkene is. In most complete way of writing the structure, you need to show where the alkene is. Here I have a 3-ethyl 3-octane. So as you see here, the main problem with the right I have already mentioned in the lecture section that alcohols get a priority. That means the alcohol should have a lower number than where the double bond is. So let me first draw what the idea or the structure related to this, what's given in here. So it is an octane, so that means an 8 carbon. I will do 8 carbons. 1, 2, 3, 4, 5, 6, 7, 8. And here it tells us that at 3 position you have ethyl. So if I count from here, 1, 2, 3, ethyl, that is fine. And at 3 position you have the N, octane, 3 ethyl, 3 octane. So it is just to say that the double bond is at 3 position. So 1, 2, 3. So that would be a 3 position. And at 5 position you have the alcohol. 1, 2, 3, 4, 5 are the alcohol. So here is the problem with this. I think what we need to make sure is that this is the alcohol should get the most priority. So that means if I count from this side, 1, 2, 3, 4, 5, the alcohol will be at 5 the way I written here. But the right one is 1, 2, 3, 4. That should give the alcohol a 3rd position for the alcohol and a 5th position for the alkene and a 6th position for the ethyl. So let me write this out now. So it should be written as a 6-ethyl, 6-ethyl, and 1, 2, 3, 4. At 5 you have, this is 1, 2, 3, 4, 5, 6, 7. So this is an octane. 6-ethyl, oct because it's 8, so it's 1, 2, 3, 4, a 5 position, 5N, the alkene, and the alcohol is now the basic. So alcohols always get a priority, high priority. So the name of the compound should end with all. So 1, 2, 3, 4. It is a 4-all compound. So the way we should name this is completely wrong because 6-ethyl oct 5N for all is the right naming for that compound. That is B is why that's incorrect. The third one, we have 2-butyl, 3-methyl, 1-pentene. Let me write the way what was given here if the structure matches to this. So if I have a 1 pentene, that means a 5 carbon. 1, 2, 1, 2, 3, 4, 5. So 1 pentene, if it is 1 is right here, it's there. 3 methyl group here. And you have 2 butyl. 2 butyl is 1, 2, 1, 2, 3, 4. So this is what this C is suggesting the structure for it. If you just look at this, the longest chain that contains the alkene is 1, 2, 3, 4, 5. No. Let me see. 1, 2, 3, 4, 5, 6. So instead of a pentene, this compound actually is a hexene. That's the problem with this. So the names this should be named as would be, this is a 2 position. We have this substituent, which is an isobutyl at 2 position. So this is 2 isobutyl, 2 sec-butyl, actually, 2 isobutyl, and it is a 1 pen, 2 isobutyl, 1 pentene. 1 pentene. So this would be the appropriate, no pentene. Sorry, that was the problem. This is 1 hexene. So in this case, the problem with this is not choosing the right branch, which contains the alkene. The longest chain is a hexene, not a pentene. So that was the problem with this. And in this D, I see Z, 2-methyl, 2-hexene. What do they want to show in this when they name it like this? 2-methyl, 2-hexene. Okay, let me do a hexene. Okay, this is A, this was B, this was C. Now for D, you have Z, 2-methyl, 2-hexene. Let me put 2-hexene as a Z, 1, 2, 3, 4, 5, 6. So it is Z as this position, and it is 2-hexene, and 2-methyl, 1, 2. So this would be a methyl group. So this is 1, 2, 2-methyl, and 1, 2, 3, 4, 5, 6. That's actually like that. 1, 2, 3, 4, 5, 6. So that structure is correct, except the only thing I can see is instead they didn't show the stereochemistry. It should have the number here. So instead of just saying Z, they should say 2Z to show that the hexene, the double bond, which is a Z isomer in a diastereomer, is at 2. So they should include 2Z in the parentheses and write it as 2-methyl, 2-hexene. That I would think is the correct name. You should have in the parentheses the numbering. Here also, I think right outsetly, I can see this is a 1. You should have a 1 also for this one, but it may not be the only problem. Let me see. So it is 1 isopropyl, 1 isopropyl, 1 butene. Okay, this is for E. 1 isopropyl, and it is a 1 butene. You have 1 as that position, a double bond, and it is an E, and it is a butene, 1, 2, 3, 4. So that's just the chain they are referring to, but at 1 position they have isopropyl. So this is the 1 position. Isopropyl is this. So you cannot name this as a butene. obviously, because the chain is not like 4 carbon. If you just count starting from here, for example, 1, 2, 3, 1, 2, 3. So I will count from here where the metal group is. So it is a 3 metal, 2 metal, 3 is the double bond where it is. So the naming would be 1, 2, 3, 4, 5. It is a hexene. So the way I will name this would be 2 metal, 2 metal. This is for D. This is for C. This is for B. This is for A. Okay, this is for E. So it is 2 metal, and it is a hex. A hex, that means a 3 hex, 3 in, and a hexene. So I can actually, since it doesn't have alcohol or anything, we can just say 2 metal, 3 hexene. 3 hexene. So this structure, instead of so I will also include the E for this compound. So what I would do is at 3E, 3E, 2 metal, 3 hexene. So there are several issues with this naming. It's not a butene, it is a hexene, 1, 2, 3, 4, 5, 6. And the numbering for the double bond is at 3 position, it is a 3E, and so on. So that's how I would correct the naming for E. How about for F? So if you have 5-methyl cyclohexene, what does that mean? Cyclohexene for F, that's for F, 5-methyl cyclohexene. 5-methyl cyclohexene is something like this: 1, 2, 3, 4, 5. 5-methyl cyclohexene. This is what they want to say, but that's not how you should write the structure. There is no 5-methyl cyclohexene. You could have 1, 2, 3, 4. Actually, instead of 5-methyl cyclohexene, this should be written as 4-methyl cyclohexene. There is no 5-methyl cyclohexene. You cannot have that because you can go this way, the shortest path, rather than going to the longest one. So there is no 5-methyl cyclohexene. Okay, the last one, G, it shows 4-isobutyl 2-methyl cyclohexene. For isobutyl 2-methyl cyclohexene, this is the structure in G that is possible, but the problem with this structure is that the methyl group, where the alkene takes the priority, carbon number 1 should be this, where it is a substituted alkene. That's where you should start. So if you start from there and count over the double bond, it will be 1, 2, 3, 4, 5. So the naming for this should be 5-isobutyl. It's a 5 position, and 1 methyl cyclohexene. So methyl cyclohexene. So it is a 5-1 rather than a 4-2. The reason being that the substituted position of the double bond is counted as priority 1, or the counting should start right there. So it's 1, 2, 3, 4, 5. So it's a 5-isobutyl 1-methyl cyclohexene. So with this, we'll conclude with the correction of the names for this alkene compounds, and we'll continue more on this. All right, let's move on. So I have 4 compounds. All of them are epoxides. And it's asking us name these epoxides as alkene oxides, meaning that these are epoxides, but they are derived from alkenes. In the future, we'll learn about how epoxides are formed. Epoxides are formed from corresponding alkenes. So they could also be named as alkene oxide. For example, this is in the future, we'll learn that this is probably generated from that kind cyclohexene oxide, the epoxide. That's why how also you want to name them. For example, this particular compound is derived from that. By epoxidizing this alkene, you can make that. By epoxidizing this cyclohexene, you can make that. This also is derived from one, two, three. At 3 position, I have. Oh, why do I have to do? So that is at 3 position, and I have 2 carbons. So this is actually synthesized by epoxidation of this alkene. So you convert it to alkene oxide. That's why the question is asking you to name it as an alkene oxide. This epoxide is generated from this 5-membered alkene. We have a 30 butyl group here. I'm just adding some context to why we are saying alkene oxide. So, for example, this one is named as an alkene cyclohexene oxide. So the name would be, you have a 1 position epoxy or as oxide, 2 position. So you have a 1, 2 position, 2 position, you have ethyl group. So this is named as 2-ethyl cyclohexene oxide. So that's how the name came. Cyclohexene is what produced this if you were to do synthesis. And here I have also a 1, 2, 3 position. So this is 1, 2, 3, 4, 5, 6. So this is a hexene oxide. So it's a hexene oxide, but at 2 position you have methyl group. So you would say 2 methyl, 2 methyl, 2, 3, where the oxide is, hexene oxide. Hexene oxide. So this also shows you the relationship, how you can convert a cyclohexene compound to epoxide. We'll learn that in the next oxidation chapter. So you can oxidize this from this alkene. So if, in the future, it could be also asked, how do you make this from this? So this is just that. So, or suggest a compound that can be transformed to this. So you just pluck out the oxygen and make it into a double bond. That's how you would start to make that. C is a little more involving because the stereochemistry is defined. Here you have 1, 2, 3 position, 4, 5, 6, 7. So it is a 3R. This position is a hydrogen coming out. So I want you to assign that. This is 3R position, that carbon. And this is also 4R. So it is a 3R, 4R stereochemistry. You need to include that as well. And it's called, totally, it has 7 carbon. 1, 2, 3, 4, 5, 6, 7. So it is heptene oxide. So 3, 4 heptene oxide. 3, 4 heptene ENE oxide as an alkene oxide. From this one is from where it came. This is from where it came. So this one is a little much easier. It is a 1, 2. If you say 1, 2, 3, 4, so it is a 4 tertiary butyl. For position, you have a tertiary butyl. This is a T-butyl group. Tertiary butyl. Butyl. Cyclopentene. This is a 1, 2. 1, 2. Cyclopentene oxide. So this is a cyclopentene that gave rise to this epoxide. So this are how the epoxides are named as alkene oxide, because they are derived by synthesis from the cyclohexene. You can convert it to epoxide. That is the context of this question. Okay, here we have an interesting, very big natural product isolated from mold. It's very toxic. It's called Bongkrekic acid. It's very toxic. It's isolated from a mold. And now the question for this is, as you see, it has alkenes, double bonds everywhere, and also it's a triacid. It's a triacid compound. And the main important question are for us to label E and Z, each one of the alkene, by just putting an E and Z label, the first thing. So I'm gonna just make sure that we label them correctly. So in this one, for example, you have the acid group, a priority group, is up, and here hydrogen is down here. Between this one and this one, the priority would be obviously this is the priority, because this carbon has a CH2 while this carbon has a carbon-carbon bond. So as you see here, the priority is up. Priority is up there, so it is a Z configuration at that point. It is a Z. And so let's see here. I have a carbon and hydrogen here, a carbon-carbon. So that is still correct. And this one, this is an E isomer. This is an E isomer. This is a Z isomer. Here I have a Z isomer. And I have here, as you see here, this is down, and that one is up. So that should be an E isomer. So as you see, we were able to assign using Kahn-Ingold priority assignment for E, Z. So I have 1, 2, 3, 4, 6 double bonds. Okay. And now the next question is to assign the stereogenic center, that is a chiral center. Here I have, this is a methyl group, this is hydrogen, so 4 different groups. Stereogenic center, and this is another stereogenic center. So I have 2 stereogenic centers. So 2 stereogenic centers. The first one, it is an S. I want you to assign that. And the next one is an R stereogenic center. Now, the question is, how many stereoisomers Bongkrekic acid would have? How many different stereoisomers? So just based on the 2 stereogenic center, you have N equals 2, that means 2 stereogenic center. If you remember our formula, to the power of 2, you have 4 stereoisomers possible for just based on the chiral center. But you have Z, E, E, Z, so you have 6 of them. So for this, you have a Z, E, E, Z. So I have 1, 2, 3, 4, 4, 5, 6. 6. Let me see. 1, 2, 3, 4, 5, 5, 6, 7. How did I have a 7? 1. Oh, here I have also one more, which is an E isomer. So there are 7 of them. So if I have 7 stereoisomers, meaning 7 double bonds, each one can have a Z and E, Z, E, the opposite. For example, here I can have E, I can have Z, I can have Z, Z, E, and so on. So for the 7 of them, I can have 7 times 2, 14 stereoisomers. As E and Z. That means the double bonds can have both possible stereoisomers. 14. Each one of those are also can be, there are 4 stereoisomers. So 14 stereoisomers of E and Z type times 4 stereoisomers of R and S, or the diastereomeric relationship. There could be 56 different stereoisomers for this compound. So you could have 56 different stereoisomers of this compound. 4 of them come from R and S, from this and that, by variation of this can have SR, RR, SR, SS, and so on. So there would be 4 of them. And E and Z, here you can have an E, you can have a Z, you can have a Z, you can have a Z, E, and so on. So you could have different compounds that are a different combination at the same time. So 14 times 4, 56 compounds, stereoisomers are possible. Okay, moving on, we are given a C₆H₁₂ compound, and we are asked to draw all possible stereoisomers with 1 double bond, that means 1 degree of unsaturation, and a metal substituent. 1 is a substituent. That means a 5 carbon, but metal would be substituted anywhere. So the possible ones are like this. So the first thing I did is metal position and the alkene at 1 position. So this is a 2 metal, 1 pentene compound. So it's a compound. Here I have a 2 metal again, 2 metal, but in this case 2 pentene position. So if I just look at these two, those are 2 different compounds, 2 stereoisomers, but you can here you have metal group, so you can't have E or Z isomer for this. So these are 2 standalone compounds that are possible. In the second row, what I did is I shifted the position of the metal group to the 3 position, and also that possibility would give me for the alkene to be at 1 position or at 2 position. So at 1 position, the only stereoisomer that we can have is the R or S stereochemistry on carbon number 3. We can have R or S for that one. In this second one, there is no stereogenic center, but these two metal groups can be E or Z possibility, because E and Z are possible. In this case, for example, this is a metal group down the ethyl group, so this is an E1. If the metal was this side and ethyl was this side, that would be a Z. So E and Z are possibilities. So how many compounds I have? I have 2 compounds of those from top. Here I have 2 and 2, 4 compounds, 6 so far. And for this one, what I did is I removed the methyl group to a 4 position, 1, 2, 3, 4 position, 4 methyl, and I left the alkene here, but I moved the double bond to 2 position, which I don't have any other which looks like that. For example, let's name this as it is. So this would be 1, 2, 3, 4. This is 4 methyl. 4 methyl. 1, 2, 3, 4 methyl. 1 pentene. And for this one, 4 methyl. 4 methyl. That would be 1, 2, 3, 4, 5, a 2 position pentene. So basically 4 methyl, 1 pentene, 4 methyl, 2 pentene. They are different compounds. What are the stereoisomers that are possible? For this one, I cannot have R and S for this because that is not stereogenic center. That has 2 metal groups the same, so that will not be a stereogenic center. But here I can have the E and Z for the double bond, no stereogenic center. So there are E and Z possibilities for that, and no stereogenic center up to that point. So how many compounds I have right here? I have 1 here, plus 2, 3 compounds here. So what are the other possibilities? If I shift the double bond here, it would be the same as that one. So unique compound. So E and Z, and I think we have 6 plus 3, 9 compounds at least. 9 compounds. At least we can write 9 stereoisomers or 9 different compounds of this C₆H₂. So you can exercise if you could write any other stereoisomer, that would be nice. So 2 methyl 1 pentene, 2 methyl 2 pentene, and 4 compounds out of this one, 3 compounds out of this one.